Okay, on these problems, I would encourage you to basically try these, maybe pause the video or go ahead and start trying these. And if you get stuck, play the video and figure out what there is going on. But I'll go through them just to make sure everybody knows how to do them. Notice that on this first one, we have an inscribed arc, an intercepted arc for this inscribed angle of TUV. So if the angle is 30 degrees, the angle is half of the arc. Well, that also means that the arc must be twice as long as the angle. So if this is 30, this is 60. And I kind of think of it like a pair of tweezers because these look like tweezers to me. So this is the skinny part of the tweezers. So you know this one has to be the small number. And then this one has to be the big number. So the arc is always bigger than the angle for all of these intercepted arcs and inscribed angles. On this next one, we see the arc here, which means the angle goes there. And if you've got something to mark and color with, that might be helpful to you. So now 84 is the big value because it's on the big side of the tweezer. So the little angle there should be half of 84 or 42. Now, some of these you have to do a little bit of work to be ready to get the problem. Like on this one, for example, you have to pull out what we talked about last week because you have the circle is 360 minus 70 minus 120 because the whole circle adds to 360. So subtract the 70 and the 120, and that should leave you with 170. And once you have 170 there, if this arc is 170, the angle would be half that arc. So half of 170 is still pretty big, but in this case, you're going to get something that I believe that's 85 degrees. So just less than a right angle there. And always check and see if these diagrams are drawn to scale. It's okay to check and see if they're reasonable. Like that looks like about 70 degrees. That should be a little less than a fourth of a circle. 120 degrees should be about a third of a circle. So since it's drawn to scale and that looks close to a right angle, you would expect it to be close to a right angle. Okay, let's see if we can scroll and do a few more. Next one. This is another one where you might have to do a little bit of work. One thing to notice here is that you have a diameter of the circle. Anytime it goes through a dot, that means the center. So you know that this is 180. So if this is 180 and this is 160, you could add those together, subtract from 360 and get 20. Or you could think, hey, NL would also be a semicircle, so you could just do 180 minus 160 and get 20. But once you have that as 20 degrees, basically this over here, the skinny part of the tweezer, the inscribed angle, is half of that arc, so it's 10 degrees. Got some more here with some inscribed polygons. Remember we said that the opposite angles of an inscribed polygon had to add to 180, so I could do n plus 100 would equal 180. And that means angle M would be 80 degrees, which once again looks reasonable. And on this other one, I would have M plus 65, the two that are opposite. Remember, opposite means across from each other. So M plus 65 equals 180. And then that would give me, let's see, 115. If you wanted to double check that, you could say if I add 100 plus 65 plus 115 plus 80, does that add all the way up to 360? Does that add up to, because the angle's inside a quadrilateral, you might remember do add to 360. So several ways to do that. On this next one, it is going to be true that J plus L, the two that are across from each other, should add to 180, and also that K plus M should add to 180. So you can go ahead and try that. One last one on this one, it wants to know if it's a right triangle. So to figure out if that is a right triangle, if this is 30, notice that's the skinny side, so this is 60. So this would have to be 180, meaning that if this is a semicircle, this is a right angle, so that is a right triangle.